Welcome back, guys. In this video we'll look at the recent IGCSE February-March 2025 paper, and as always with these past paper videos I would recommend, as well as watching this video, make sure to also check the mark scheme, and of course if the video is too slow then you can watch at 1.5 or 2 times the speed. Okay, so question 1 says complete the sentences about number systems, use the items from the list. Some of the items in the list will not be used and you should only use an item once. Okay, and what we just got a load of, well, letters and numbers. Right, so the binary number system is based, well, that's going to be 2, I think everyone should know that. Right, the smallest denary number that can be represented as an 8-bit binary number. Right, so of course, well, this depends on if we're using signed or unsigned. If we're using unsigned, well, then of course it's going to be positive only. Right, if we're using signed, well, then it can be positive or negative. And of course, signed is also called 2's complement. Right, so let's actually just recap the ranges. Now, the formula for the range, okay, so the smallest in unsigned, of course, is just going to be 0. Right, the biggest in unsigned, well, that's going to be 2 to the, okay, so the biggest in unsigned is, what, 2 to the n minus 1. Right, so if using 8 bits, well, that's going to be, 255. Alright, and of course, what n, right, okay, so n, of course, just being how many bits we're using. And if we actually think about the bit patterns, now I'm going to do this just in 4 bits, right, because otherwise it's sort of too much. Right, now of course, well, the bit pattern for 0, well, of course, just 4 zeros. And the bit pattern for the biggest unsigned number, well, that's just going to be all 1s, right, so 4 1s. Or if you're using 8 bits, right, of course, 8 1s. Right, now if we're using signed, right, signed is a bit more complex. So what we want to do, okay, the smallest number, well, it's going to be minus, right, here is going to be 2 to the n minus 1. Right, now if we're using 8 bits, okay, well, because we then do n minus 1, okay, of course that's 7. So, right, okay, so basically what that's going to be, well, negative 128. Right, and then if we're thinking about the positive number, or the largest positive number, what that's going to be 2 to the n minus 1, right, and then we also have a minus 1 here. So that's going to be, what, positive 127. And the reason we have the negative 1 and the negative 1, well, basically that's because one of the bit patterns is used by 0. Alright, and if we think about the bit patterns for this one, so the most negative number, or the smallest number, well, that's going to be a 1, because of course we want the negative part, right, and then, okay, so basically we want the negative part, alright, and then we don't want to add any positive numbers to it, right, so, okay, so of course that's going to be a 1 followed by zeros. Right, if we look at the biggest positive number, well, that's of course going to be, well, no negative, right, and then, well, so all of the positive bits are therefore just going to be set to 1. Okay, so if we think then the biggest 8-bit number, right, for unsigned, well, that's going to be 255. Right, the largest denary number that can be represented as an 8-bit binary number. Okay, hang on, okay, right, so this is the smallest, right, so the smallest is 0, and the largest here, right, that's 255. Right, the hexadecimal number system, well, that's going to be base 16, right, of course, what hex meaning 6, right, what dec meaning 10. Right, each hexadecimal digit is equivalent to, right, and that's going to be 4 bits, and hopefully people can remember this. Okay, so 1 hex is 4 bits, right, and that's why it's really easy to convert between hexadecimal and binary, and of course vice versa, okay, from binary to hexadecimal. Now, sometimes I see people, and if you have a question like, I know, convert, this hexadecimal to binary, first what they would do is convert to denary, right, then they would go from denary to binary. But actually doing that is, well, so 1 is more complex, right, and also 2, it also gives you sort of double the chance of making a mistake, because you're having to do 2 conversions rather than 1. So what we can say is, let's say for example 0, well, of course, right, 0 is just, 4 zeros. Alright, so here we said, well, of course, so this left column is called hex, right, this, well, of course, just binary. Right, then if we think the biggest in hex, well, that's going to be f, right, and of course, well, that's going to be 4 1s. Alright, then of course, okay, so if you take something in between, let's say a, well, a of course is 10, right, therefore, of course, well, 10 is just going to be that, right, 8 plus 2. So that, so if you're not sort of sure about how to convert between hex and binary, I would say just have some practice at doing that. Right, anyway, the numbers 1 to 9 are used, and the number 10, right, okay, that's represented by A, right, the hexadecimal number system continues up to 15, right, which is, well, F, right, as we've seen. Right, 2 8-bit binary numbers are given, add the 2 8-bit binary numbers using binary addition, give your answer in binary, and show all your working. Okay, so what we think then, well, 1 plus 1, okay, so actually basically 1 plus 1 is 2, but if we think about that, Well, 2 in binary is 1, 0. So what we're saying, well, there's going to be a 1 in the left column, right? Or yeah, there's a 1 in the carry column, right? And then a 0 in the sum column. So here, if we do that, right, 1 plus 1, well, there's a 0 in this column, right? And then, yeah, a 1 here in the carry column, right? Likewise, 1 plus 1 plus 1, right, that's 3. So there's going to be a 1 here in the carry column. Okay, yeah, sorry. Okay, there's a 1 in the sum column, all right, and then also a 1 in the carry column. Because if we think 3, well, 3 is just, well, sort of, yeah. Okay, yeah, sorry, okay. So 1 plus 1 plus 1 is just, well, obviously, yeah, 1 here, right, and then a 1 here. Right, the next one, so, well, 1 plus 0, that's going to be 1. All right, 1 plus 0, that's 1. All right, 1 plus 1, well, that's a sum of 0, then a carry of 1. Obviously here, 1 plus 0 is 1. All right, 0 plus 0 is 0, and yeah, 1 plus 1. All right, that's 1. Okay, so with these questions, I would actually recommend checking your answer. So let's just do it quickly. Right, that's going to be 128. Right, this one is going to be 16, so that's 144. Right, that's 152. That's going to be 154. And then, yeah, I think 155. Yeah, I think that's correct. Right, then, if we look at this one, so what, that's 16, that's 2, that's 18. Right, that's 1, that's 19. Right, so here then, what is 155 plus 19? Right, of course, that's going to be 4. And right, that's going to be 7. Right, so yeah, that should be 174. And if we just check this, right, that's 128 plus 32, that's 160. Right, plus 16. Okay, hang on, so plus 8. Right, so 160 plus 8, that's 168. Right, plus 4, 172. Yeah, plus 2, right, 174. Yeah, again, so in the exam, I would recommend, right, checking your answers, yeah, just to make sure. Right, then C, binary addition can result in overflow. Tick one box to show the correct definition of overflow in binary addition. Okay, so let's just explain overflow if people don't know. Right, so overflow, this occurs when you have 2 operands of the same sign, and when you add them, they result in an answer that has the opposite sign. So to be specific, okay, okay, so let's say you have a positive number plus a positive number, right, and the answer becomes negative, right, or if you have the opposite, okay, if you have a negative number plus a negative number, right, and the answer becomes positive. Alright, and if we think about 2's complement, well, that's of course what when we've got our 0 plus 0, and you know, we sort of get a 1 in this, yeah, most significant bit column. Right, or if we have what 1 1, and then obviously, well, okay. So if we have 2 numbers, you know, starting with 1, and then the answer starts with a 0, because of course, yeah, we've got some, you know, carry out in this leftmost bit. Alright, and I think, I mean, that actually makes sense. Like the way, okay, so the way I like to imagine it, if you think of a number line. So let's think of a number line, and we'll use 8 bits. Now the smallest number, as we saw, is going to be what, minus 128 with 8 bits. Alright, and actually, okay, so this is if we're thinking about 2's complement. Right, the biggest number, well, that's going to be 127. So let's imagine we have a positive number, right, for example, 127. So let's say we're starting on 127, okay, and then we add a positive number. Well, then we're going to be going this way, right, which is going kind of off the number line, right, so obviously too big. Likewise, if we have a negative number, let's say minus 128, right, then if we add another, okay, so if we have a negative number and then add, you know, another negative number like this, well, possibly, you know, that can go too negative. And this is why we can never have overflow if adding operands of different signs, because let's say if we have a negative number like minus 128, well, if we then add a positive number to that, right, then of course that's going to be going towards 0. Right, likewise, if we start on a positive number like 127, right, if we then add a negative number to it, well, then again, the answer is going to be going towards 0. So yeah, then of course it's always in that fixed range. Alright, so yeah, okay, and I guess actually another definition for overflow, you can say when the answer requires more bits than the number of bits you have available. Right, so let's sort of read through these and see which one kind of matches up best. Right, the answer has created a negative number that cannot be represented in binary addition. Yeah, okay, so I think this one is not really correct, because, okay, so I guess overflow can obviously, yeah, wrap around into negative, but you're never really going to get a negative number that's kind of outside of that range if adding 2 positive numbers. Yeah, and I think here, I mean, again, right, okay. So if we look at this example, I mean, they are kind of talking about unsigned, really, I think. Right, okay, so B, yeah, the answer is the result of a logical a logical shift that cannot be performed in binary addition. Well, I mean, logical shifts, obviously, that's something completely different, right? Just, yeah, moving the bits left or right. Right, the answer is too large to be represented in the number of bits available. Right, or D, the answer is too small to be represented in the number of bits available. So to be honest, actually, like, this question is kind of weird because, to be honest, both C and D are correct. But I think maybe for this question, because they're sort of talking, yeah, I guess about unsigned, right, then I think we can probably go with C. But yes, right, okay. Like, I still think generally you want a more sort of general definition where you can say, well, either when you're adding two operands of the same sign and the answer has the sort of opposite sign, right, or where the result kind of requires more bits than the number of bits you have available. Yeah, it's probably, yeah, okay, which is kind of this. All right. So if we go to, right, an artist creates an image on a computer, state what is meant by the color depth of an image. Okay, so the color depth, this is the number of bits used to represent the color for each pixel. So yeah, let's say that, let's say, right, the number of bits, yeah, okay, and yeah, sort of excuse the terrible handwriting. The number of bits right, used to represent the color. Yeah, let's say what of each pixel. Yeah, I think that should be okay. Right, then describe the relationship between the resolution of the image and the file size of the image. Okay, so here I think we can talk about the formula, right? So the formula for image size, well, it's going to be the resolution, and of course the resolution being the number of pixels in the image. Right, then that's going to be multiplied by, yeah, okay, so that's going to be multiplied by, well, the color depth, okay, and of course, well, that's the number, yeah, the number of bits, you know, for each pixel. Okay, so what we can say is basically, well, if we increase the resolution, then the file size will increase kind of, you know, sort of, well, directly proportionally to that. So if we double the resolution, then we're going to get a file size that's twice as big. So yeah, let's mention that. Let's say since, right, since what the formula, right, the formula, yeah, and then, yeah, for image size, or yeah, image file size, right, for image file size, right, is, and what that's going to be resolution. Okay, right, resolution, let's go, right, multiplied, right, and that's going to be what the color depth. And actually, I think for resolution, I'm going to put in brackets, well, that's the number of pixels. Right, yeah, number of pixels, right, multiplied by, well, the color depth. Alright, and the color depth you can also call the bit depth as well. So the color depth, and I'm not really going to give the definition again because we've sort of done that here. Right, okay, so since the formula is, yeah, resolution times color depth, right, let's say then, I guess what, changing the resolution, or in fact, actually, okay, yeah, so let's go increasing. Right, let's go then, yeah, then increasing the resolution, yeah, will increase, right, increase the file size, right, file size in direct proportion. Right, and I think let's give an example. Right, let's say e.g. Right, e.g. what, double, okay, yeah, okay, alright, so let's say doubling the resolution. Right, doubling the resolution, right, will double the file size. Right, okay, it says the artist compresses the image file before uploading it to their website. Users can download the image file from the website to print as a poster. The image is compressed using lossless compression. Explain the reasons why the artist chose lossless compression instead of lossy compression to compress this image file. Right, okay, so I think maybe first we can just sort of mention kind of briefly the definition of lossless compression. So we can say, yeah, right, okay. So lossless compression, well, what you'll be able to create an image that's, you know, still high quality. Of course, you can get the original image back, right? But at the same time, you're still going to sort of save memory, or yeah, save storage space, compared with if it was not compressed at all. Yeah, okay, that was, I think, a terrible definition. Yeah, okay, all right. So let's think maybe if we can word up a bit better. Let's say maybe since, or in fact, actually, okay, so let's say lossless. Right, lossless compression. Right, let's say will. Yeah, I guess what will reduce, right, the file size. And I think for these kind of questions, I mean, you want to sort of bring it back to the example. So if they're talking about a website, well, why would they want to reduce the file size? Right, one, because it's going to use less storage space on their web server. Two, it's also going to be faster for users to download. And I guess three, it's also going to sort of use less bandwidth on their part, because maybe each month they have like a limited amount of bandwidth. Therefore they can't send sort of like terabytes and terabytes of data. Right, okay, we'll reduce the file size. Okay, alright, let's say which. Alright, which will mean what less storage is used on the web server. Right, is used right on the web server. Okay, alright, let's also say downloads. Alright, downloads will be faster. Okay, so downloads for users. Okay, so I think first maybe I'll talk about for the web server. So let's say downloads, right, will use less bandwidth. Right, and be faster for the users. Faster for the users. Right, okay. Yeah, I think that's okay, right? Then we can say what the users will be able to, decompress and get the original high quality file back, which I guess they'll want, since they want to print it as a poster. Okay, right, let's say, when decompressing. Right, when decompressing, the users right, will be able, alright, so let's just say will obtain the original, high quality, high quality image, which they will need, or, alright, so let's say, I don't know, which is ideal, ideal, for printing, ideal for printing, let's say as a, I'm going to put in brackets large, because maybe the poster isn't that large, but so let's just say poster, because honestly, like a lot of posters, maybe it's going to be A3, right, maybe it's going to be bigger, so this could be quite large, which in that case, then of course you do want a high quality image, because if it's not high quality, so if it's not high quality, then as you scale it up, of course, then you're going to see more and more sort of like blur, sort of pixelation and things. I think that's okay. I mean, we could also mention that if, let's say, the artist is just, I don't know, some hobbyist, right? They're, so they're probably not going to have, like sort of millions of people downloading their artwork. Likewise, they probably also don't have, sort of like thousands upon thousands, or gigabytes and gigabytes of artwork that they're uploading. So in that regard, they probably don't have to worry about storage space on the server that much. And I guess, likewise for downloads, right? So they don't have to think, I need to, sort of compress as much as possible, right, using lossy. Let's maybe say that. Let's say, what if the, if the artist, if the artist, I don't know, doesn't have, I guess, like thousands of, thousands of works, or, I guess, huge numbers, right, let's say if the artist doesn't have very huge numbers, right, let's say, of artwork, right, or, I guess, sort of, I don't know, like users or, visitors, okay, so if they don't have huge numbers of artwork or visitors, let's say then, they won't need to, use lossy to compress as much. They won't need, right, to, I guess, compress more using lossy. Right, compress more, right, using lossy compression. Right, we can say, I don't know what, image quality is more important or something. Right, image quality, is more important. And I guess here, I've written quite a lot. Now, obviously, if I was writing with a pen, rather than on this graphics tablet, right, probably that would use more space. It probably wouldn't use this much, right? But I will say, some people think like, right, okay. So some people, okay, they'll see a question like this, and what we see just 3 marks, and like maybe all they're right is just, I don't know, you know, 2, 3, right? Yeah, okay. So let's say 2, 3, right? Maybe 4 lines. But if you think, I mean, these exam papers, I mean, it's always better to write too much. Yeah, even if you have to go on, you know, the side of the paper or something. Yeah, it's always better to write, you know, too much information, right, rather than not enough. Yeah, because I guess the examiners, I mean, really, they're just kind of looking for the keywords. Right, anyway, so the next we want to describe our chosen method, and right, this is going to be one lossless method of compressing an image. Okay, so if we think a lossless compression for an image, well, really, that's just going to be run length encoding. Right, okay, yeah, run length encoding. Right, now the way that works, I guess we can say what consecutive pixels of the same color will be converted into the count of that number of pixels, right, followed by the color value. Yeah, I think let's say that. Let's say, I guess, what, repeating? Yeah, okay. So actually, okay, let's not say repeating, because even if it's a single color, right, then of course we still need to go, I don't know, yeah, 1 red, right, 1 blue, you know, 1 like yellow, for example. Right, so let's say, I guess, what, pixels? I guess, okay, alright, so let's say pixel values, right, pixel values will be replaced. It will be replaced, let's say, by what, the count, right, the count of the, I guess, what, of the number, right, of consecutive pixels of that color. Right, consecutive pixels, yeah, I guess, what, with that color value. Right, with that color value, right, I guess, what, followed by the color value itself. Right, followed by the color value itself. And I think for these questions, it's always good to give an example, right? Let's say e.g. I guess, I know what, okay, let's say like red, I know, yeah, red, yellow. Right, let's say, I know, yeah, okay, right, let's go like yellow, right, and let's say blue. Right, okay, so, yeah, let's say what would be replaced, right, would be replaced, or I guess what, encoded. Yeah, okay, right, let's say encoded, right, let's say as, and what that's going to be, what sort of, well, 1 red, right, 1 red, 3 yellow, and 1 blue. Okay, and if we just think quickly, now if they were asking for lossy, well, really we just want to think of the formula, and we said what the formula was, resolution times color depth. Therefore, we can reduce either of those to reduce the image size. So, of course, while reducing the resolution, or just using less pixels, making it smaller. We're obviously reducing the color depth, well, that's basically using a kind of, I guess, less unique colors, right? So rather than having, let's say, 24-bit color, and I think what 24-bit color, I think that's like, is it 16.7 million? Yeah, I think it's about 16.7 million. So rather than using, say, 24-bit color, well, we could reduce that, I don't know, yeah, okay. So let's say we could reduce that to, you know, 8-bit color. And of course, okay, yeah, so in that case, well, that's only going to use, what, a third as much. Right, and I guess what 8 bits is going to give us, what, 255 unique colors. And to be honest, actually, another kind of, I guess, indirect benefit of using a lower color depth is that because the colors will be sort of rounded to a, I guess, kind of similar color, right, then you can actually use run length encoding more effectively. Because let's imagine we have a color, let's say, I don't know, yeah, FF, let's say 0001. So FF, well, this is the red part, well, 00, that's the green part, right, 01, that's the blue part. Now, let's say you have this pixel, and then the next pixel is, I don't know, yeah, FF, right, 00, and then, well, 00. Now, the thing is, okay, so because, obviously, so because this one is obviously not equal, you know, to this one, well, then we can't use run length encoding. But if we like actually reduce the color depth, well, then basically what's going to happen, I mean, probably these are going to be kind of reduced to the same color. So actually, so this one will probably become, you know, FF0000, right? And now because they're going to be sort of the same, well, of course, so now we can actually use run length encoding on these as well, to get that additional compression. Alright, anyway, the next one, so the artist emails the image file to their friends, explain how a file is broken down into packets and transmitted over a network. Okay, so first I guess we can maybe talk about what's in the packet. So there's going to be the payload, right? Of course, the payload being the data. There's also going to be a header, and that's going to contain what the source IP, the destination IP. And if we're using TCP, right, the transmission control protocol, then it's also going to contain the packet number. And the packet number, I guess actually the packet number, well, let's mention in a minute. Okay, right, and I guess there's also going to be a trailer. Right, and the trailer, well, that's going to include some sort of error checking, integrity checks. You can say like a checksum, right? There can be a cyclic redundancy check, right? CRC, basically just sort of kind of having a count of how many ones there are. Yeah, and if there's a different number of ones, well, then it can, right, okay. So if there's obviously a different number of ones, you know, that the receiver gets, well, then the receiver knows that there must have been some corruption. Okay, right, then if we talk about how it's actually sent, so what the packets are obviously sent to routers. The router will use the destination IP address of each packet. It will then look in its routing table and it will forward the packet on, you know, to the next hop. And I guess, well, that routing table could be static, so it's kind of pre-programmed in, you know, where to send it, right, or it can be dynamic, where the router will actually kind of try to figure out the best route to send the packet on. Based on, for example, how much traffic that other routers have, yeah, based on, I don't know, if there's some sort of network, like network issue or something. Okay, so you can say, yeah, the router will try to find the optimal route. Right, and then when the receiver gets it, right, okay, so again, if using TCP, right, when the receiver gets the packets, well, one is going to have to make sure it's got all the packets. Okay, any packets it doesn't have, it's going to have to ask for them again. And of course it can do that based on the packet number. So if we receive, right, packets 1 and 3, but we don't receive, you know, packet number 2, well, then of course right, okay, so then of course, you know, packet 2 is going to be like resent. Right, okay, the packet number is also used for the reordering, because the packets can be sent at different routes along the network, right, therefore they may arrive out of order. And if they arrive out of order, well, then of course they have to be reordered at the end. And actually I say of course, okay, but that's only if using TCP, because TCP, well, one, we want to make sure all the packets arrived, two, we want to make sure all the packets arrived, you know, in the correct order, because let's say we're, I don't know, sort of downloading an image or downloading a web page, well, if we, you know, don't have some of the packets, well, then of course we're going to sort of miss some of the image. Or yeah, if okay, so if they're in the wrong order, well, then of course, yeah, the image is going to be corrupted, or yeah, the sort of, you know, web page is going to be corrupted. Right, however, if using UDP, right, so I think the user datagram protocol, and that's used, I mean, mostly just for media, right, so let's say for audio streams, and I guess, well, video as well. Let's say you're having like an online phone call, so yeah, what, voice over IP. Well, if you don't receive some of the packets, then you actually don't have time to go back and, you know, kind of re-request some of those packets, because at that time, while that audio has already played, that's kind of like you're sort of going back to get the previous word that the person has said. Same with video. Okay, if you don't get some of the packets, right, if you don't receive some of the video frames, you can't go back and re-ask for those video frames to be, you know, resent, because of course, well, what's going to happen? I mean, right, okay. So of course, like, those video frames are in the past, and I guess sort of, yeah, some of the current video has, you know, already played. Alright, so let's try to explain that, and yeah, there's going to be quite a lot here, 5 marks, right? They've given us about 10 lines. So we can say what the file, the file, let's see what will be broken, broken down, broken down, right, into many small packets, right, many small packets, right, let's say containing, containing, right, a header, let's say which stores, right, which stores, right, the destination, or in fact, so let's say the source and destination IP, right, the source and destination IP address, right, let's say, as well as what the packet number, right, the packet number, and let's say if using TCP, if using TCP, because again, UDP is not going to have the packet number. Right, okay, let's say also, the payload, right, the payload, well, that's going to be the data, right, data, yeah, I guess, well, will be included. or in fact, okay, all right. So I think let's combine them. All right, let's say also the payload, right, and trailer. Right, okay, let's. All right, and actually, I think for trailer, let's explain. Let's say what containing. Let's say containing, I guess, what error / integrity checks. Yeah, let's say that, right, error / integrity checks. Right, will be added. Okay, right, then in terms of how it's actually transmitted, let's say what packets will be sent to the router. Right, packets will be sent, yeah, to the router. Right, let's say which. Right, okay, yeah, which will use, and I guess we say what the destination IP address and its routing table. Right, we'll use the, okay, alright, so let's say we use the packet's destination IP. Right, we'll use the packet's destination IP, right, and, well, I guess its routing table. Alright, and when we say it's, of course, right, yeah, okay, so it's here is referring to the router, okay, so yeah, the router's routing table. Alright, and I think I'm going to sort of give more, yeah, more detail. Let's see what can update dynamically. Yeah, can update dynamically. Let's say what to determine the optimal route, or yeah, to try to determine. Okay, let's say that, right, to try to determine the optimal route. Yeah, the optimal route, right, to send packets. Okay, right, let's say what packets may arrive, yeah, right, okay, let's say, right, packets may travel different routes. Right, may travel different routes. Right, different routes, yeah, and hence arrive out of order. Right, and hence, okay, hence arrive out of order. Yeah, okay, I guess we're at the receiving device. Okay, yeah, receiving device, let's say what which will have to reorder them. Okay, yeah, let's say, right, which will reorder them. Okay, yeah, reorder them if using TCP. Yeah, okay, so hopefully that should be enough for 5. Right, then the packets can use many different methods of data transmission to travel. Complete and annotate the diagram to show the difference between serial full duplex transmission between 2 computers and parallel simplex transmission between 2 computers. Right, okay, so serial, of course, well, that means the data is just sent, 1 bit at a time, basically just, 1 wire. Right, and then obviously full duplex, well, that means the data can go in both directions. Alright, so what we can do, let's probably draw 1 wire going from computer 1 to computer 2. Alright, and then actually I'm going to draw another wire going back, yeah, from 2 to 1. So what we can say, I guess, what bits can be sent in both directions. Let's probably say that. Or in fact, okay, so maybe we can mention the wires. Right, let's say, okay, alright, so bits sent. Okay, right, bits sent. I guess what individually, or okay, alright, let's say, yeah, 1 at a time. I guess I don't know what bits can be sent in both directions. Yeah, I guess what, bi-directionally. I mean, yeah, let's say that, okay, right, bi-directionally. Right, okay, then if we look at parallel, okay, so parallel, what, okay, yeah, so parallel, then we're going to have multiple wires, right, but simplex, well, the data can only travel in one direction, or yeah, the bits, the packets, are only in one direction. Alright, so let's probably draw about 4 wires here, yeah, just to, make it obvious, right, there's multiple. Okay, right, let's say multiple wires. Yeah, let's see what multiple wires send, I guess, well, bits simultaneously. Right, yeah, send bits simultaneously. I guess what bits or packets. All right, bits. Well, I guess yeah, will travel, unidirectionally. All right, bits travel. I guess what? Okay. All right. Yeah. Okay. So let's say in one direction, or yeah, only in one direction. Then number 3 says a computer has a central processor unit, CPU, memory, and secondary storage. The computer has a von Neumann or von Neumann architecture, and circle 3 registers that are found in the von Neumann architecture. Right, okay, so this one's a bit tricky because actually a lot of them sound kind of similar to the answers. Right, okay, so I guess the first register, okay, that's going to be here, the accumulator. Right, if we look at some of the others, I mean, yeah, they're not really valid. Right, so if we think the current instruction register, and actually let's think of the possible values. Okay, so we can say accumulator, right? We can say what the PC, the program counter. We can say the memory address register, the memory data register, right? The current instruction register, and probably they would also accept the status register. Although, yeah, that's more of a kind of A level or AS level thing. Okay, so I think here we see these three, right? Accumulator, current instruction register, program counter. And yeah, if you look at all the others, there's none there that are actual real registers. Right, so we want to state the purpose of the CPU in the computer. So I guess we can say what it's going to execute instructions based on the fetch-decode-execute cycle. Or yeah, I guess like according to the sort of fetch-decode-execute cycle. Yeah, let's say that, right, let's say to execute right, instructions. Yeah, actually, right, okay. Alright, so I was going to say indefinitely, because, I mean, basically what it's just going to continue executing instructions, I mean, while instructions are available, and, you know, of course, while the, CPU is turned on, or, yeah, while the computer is turned on. Yeah, let's say that maybe execute instructions, alright, actually, okay, yeah, so let's go according to, right, we could say like via, right, the fetch, decode, execute. Right, fetch, decode, yeah, if I can write, okay, fetch, decode, execute cycle. Alright, and actually, let's see what while the, device is turned on and instructions are alright, let's see that, okay, while the device is turned on, or yeah, while the computer is turned on, and instructions are available. Then it says computer A has a 2.1 GHz core processor, right? Computer B has 2.5 GHz dual core processor, and computer C has 5.2 GHz single core processor. We want to identify which computer is the most likely to execute more instructions simultaneously, right? And justify your answer. Okay, so I think this one basically we just need to look at how many cores they have, because if we think, well, if it's single core, okay, we can execute obviously one instruction at a time. Obviously dual core we can execute two instructions simultaneously. Obviously quad, quad is 4. Right, so that's going to be computer A. Right, the justification, let's say, since quad means 4, I guess. Right, since, quad means 4. Right, means 4. Let's say, computer A. Right, computer A has 4 cores. Let's say B has 2. Alright, C has 1. Hence 4 instructions can be entered. Hence 4 instructions. Right, 4 instructions can be executed simultaneously. Since each core can function, kind of independently of the other cores. Let's say that, right, since since each core can function independently, simultaneously, alright, let's say independently of, simultaneously, let's say with the other cores. And I think it's probably not the best wording, but I mean, hopefully that makes sense. Right, okay, then we want to explain why computer C can execute more instructions per second than computer B. Right, okay, so, and actually let's also do this for the first one. So what we're thinking, the clock rate here at 2.1 gigahertz, that's basically saying, well, how many instructions we can execute per second, right? But that's going to be on each core. because okay, so basically each time the clock ticks, well, I mean, potentially one instruction can execute. And the reason I say potentially is because, well, some instructions, right, let's say add, right, things like and or XOR, right, not, they're simple instructions, right, they can execute in one clock cycle. Things like divide, I think divide might take maybe 10 or 20 clock cycles. Yeah, that's, much more complex. Yeah, so what you can say, I guess, well, potentially, 2.1 billion instructions can execute per second, right, on each core, right, on computer A. But the thing is, I mean, obviously, since this has 4 cores, well, then you just need to multiply. So what that's going to be, I guess, 8.4 billion instructions per second, right, potentially. This one, obviously, well, that's going to be 5. Obviously, this one, well, that's, 5.2 billion, because obviously, 5.2, and then obviously single core at times 1. Yeah, so let's try and say that. Right, let's say, okay, since the clock rate, since the clock rate determines, okay, yeah, let's say what determines how many instructions are executed per second. Right, how many instructions, right, are executed per second. Right, let's say on each core. Right, let's say, yeah, then. Right, okay, let's say, well, then, yeah, I guess what then B, or yeah, computer B, right, can execute. Well, that's going to be, I guess, well, 5 billion. Right, 5 billion instructions per second. Okay, right, 5 billion instructions per second. Right, and let's actually write the calculation there, so that's what, 2.5, yeah, and I guess we can say, what, 2.5 billion? Right, 2.5 billion, right, multiplied by 2. Right, let's say while C, yeah, while C, well, yeah, okay, right, so while C can execute, right, 5.2, yeah, 5.2 billion instructions per second. Okay, so actually, I mean, I think really that's probably enough for 2 marks. We might also mention that actually this difference is probably kind of exacerbated even more. Because the thing is, right, okay, so let's say if in fact this was 2.6, now you might think, well, 2.6 times 2, okay, that's also 5.2 billion, right, therefore that, okay, so that, okay, therefore you think, well, maybe B and C are going to equal, yeah, they're both going to, execute 5.2 billion instructions per second. However, in reality, right, when you add more cores, you usually don't get kind of like a sort of 1-for-1 or kind of 100% increase, because there's also kind of additional overheads. Let's say if we have like core 1, core 2. Now maybe we have core 1 that has to yeah, okay, sorry, okay, so okay, maybe we have core 2 that has to wait for core 1 to finish, because I guess core 2 is kind of waiting for the result of that in order to use that result in its own calculations, or yeah, in its own instructions. Right, so that's kind of one thing you get, yeah, sort of core that has to wait for the other one. You also get, I guess, because you have shared cache, and then maybe, for example, one of the core is, let's say, using, say, some particular memory address, and that memory address is then going to be locked for another core. So yeah, then you get this kind of cache, I guess, like kind of cache conflict, and yeah, also cache, right, synchronization issues. So because of this additional communication, well, I think they often say that if you add kind of an extra core, right, then you get a 50% increase. So you say that a 2-core system, right, if it's running at the same clock rate, a 2-core system is generally going to be about 1.5 times faster, right, not 2 times faster. So I think we can also mention that. Let's say, yeah, I don't know. Okay, let's say, right, B. Yeah, I mean, let's say that, right, B, probably, I don't know, okay, okay, yeah, okay, let's say B probably can execute. Right, okay, B probably can execute, what, 2.5, well, yeah, 2.5 billion instructions. In fact, I mean, that's going to be quite wordy. Okay, let's say, right, B, right, also, right, is probably even slower. right, probably even slower, right, because of right, communication between the different cores. Yeah, okay, so I think that should be okay. Right, then the next one. So all three computers have the same instruction set. Define the term instruction set. Okay, so we can say what this is the list. Yeah, let's say the list, right, of all machine code instructions. Right, all machine code instructions. Right, that I guess what the processor, or yeah, the sort of processor architecture. Right, let's say the processor. Yeah, okay, right. So let's say what that the processor can execute. I mean, you could say what the I don't know, yeah, the processor's architecture or the processor family, but yeah, okay. So I think here just say processor. Right, that's fine. All right, and guys, like, okay, so if people want to see an example of an instruction set, then well, on my website, where it's going to be what asmcode.pro. Right, so to be honest, this is more for AS, although this does also yeah, okay. So this does also demonstrate, for example, the fetch-decode-execute cycle, right, showing the status of the different registers, or yeah, okay. So I guess not the status. Okay, let's say showing the values of the different registers, as you're executing each instruction. So if people are kind of confused about the fetch-decode-execute cycle, then yeah, I would recommend this site. Alright, and the reason I was mentioning this because well, on this website you can also see the instruction set for Cambridge, and for example, well, that's going to be add, it's going to be for example LDD, or I said well, load using direct addressing. Again, I mean really this is more AS, but just to sort of give an example, okay, so when we say instruction set, well, that's the list of all of the different instructions. So yeah, like add, load, store, maybe like sub as in subtract, right, and, or, XOR, right, not. Yeah, just all of those machine code instructions. Right then, number 4, an automated teller machine ATM is a device where a person inserts the bank card and can request to withdraw money. The ATM also allows the person to check how much money they have in their bank account. A sensor is used to detect when the person stands within 1 meter of the ATM. When a person is detected, a welcome message is displayed on the screen. Right, identify an appropriate sensor for the ATM to use to detect a person. Right, okay, so I think for this, I mean, we can probably say infrared, because infrared, that can be used to sort of measure their heat, right, sort of detect their heat. And then if it sort of notices that, I guess what, there's a sort of, I guess kind of an object that's kind of, yeah, sort of what, like emitting heat, right, in the shape of a human, well, then it can, probably assume it's going to be a human. I mean, something like a proximity sensor, maybe you wouldn't want to use, because I think a proximity sensor, basically that's going to detect everything. So even if you had like a lump of plastic, right, a lump of metal, a proximity sensor, right, that's also going to detect that. Whereas I guess if you say infrared, I mean, because that's really kind of measuring the heat that they're giving off, right, then something like a sort of lump of plastic, well, that's not really going to be detected. Yeah, or for example, I know like a sort of tree or a car. Right, okay. Yeah, let's say infrared then. Yeah, okay. All right, so infra. Okay, yeah, like RA, right? Right, then we want to describe the role of the microprocessor in detecting the person. Okay, so we say what the microprocessor will take the signals that are coming from the sensor, and I guess it can then use that to determine the distance, and what if the distance is less than, and I guess here it says within 1 meter, so I think that's probably less than or equal to. So yeah, if it's less than or equal to 1 meter, well then basically it can just sort of call the function, or call the procedure that's of course going to display this welcome message. Or else if they're not within that, right, then of course it can I guess just sort of do nothing. Right, let's say that let's say what sensor values. Right, sensor values. Let's say are continuously sent. Right, and actually, if you look at a lot of the past papers, this is a word they kind of always use, right, when talking about microprocessor sensors. Right, okay, so sensor values are continuously sent, right, to the microprocessor. Right, to the microprocessor. Let's say which will Okay, yeah, okay, alright, okay, yeah, okay, let's say which will, I guess what, calculate the distance. Yeah, I guess what, calculate the distance. Alright, and I'm also going to say, what, and possibly determine if the, object is a person. Because, yeah, maybe it will do this, maybe it won't. I guess it depends on how advanced the system is. I guess some systems, if you have like a, right, okay. So some systems maybe have like a bird flies in front of it, right? Maybe that will trigger it. I guess if it's more advanced, right, maybe it will look for, again, the sort of shape of a person. Right, okay, yeah, which will calculate the distance, right, and let's say, and possibly, right, check, I don't know, yeah, if they exhibit, right, if they exhibit, right, okay, exhibit what, characteristics, characteristics, right, okay, that's spelled completely wrong, but yeah, never mind, characteristics, right, of a person, and I think we can say what shape, I don't know, yeah, heat signature, right, let's say, etc. Okay, right, let's say if, so if the distance is, what, less than or equal to 1 meter, less than or equal to 1 meter, well, I guess the microprocessor will, I guess, what, call the procedure, right, the microprocessor, right, let's say, yeah, will call the procedure, right, call the procedure to execute, I guess, what, the kind of, yeah, welcome screen code or the, yeah, display message code. Okay, right, we'll call the procedure, right, to display the message on screen. Yeah, okay, I think that's okay. Alright, now probably what I would do, okay, I would also mention what's going to happen if they're not within 1 meter, alright, just to, try to be sure to get all three of these. Yeah, because sometimes they do sort of expect you to write both. Right, so if not within 1 meter, right, if not within 1 meter, I guess what, I mean, nothing will happen. Yeah, let's see, what, the microprocessor will do nothing. Alright, the microprocessor will, right, do nothing. Yeah, so I think that should be okay. Right, then we want to describe the features of the ATM that will identify or make it an embedded system. Right, so an embedded system, well, one, it's going to perform only a specific task. You say it's what kind of special purpose. Right, it's also difficult to change that. So, for example, an ATM, I mean, actually, to be honest, an ATM probably does have like a mini computer inside. So if you are, I don't know, some criminal, you could like smash the thing open, and I mean, you could probably, run that as just a regular computer. Yeah, and actually, I mean, some ATMs, I noticed that some people, they've managed to like close the ATM software, and then most of them, I mean, actually, a lot of them, they're still using like Windows 7, right, as the operating system. Right, but anyway, okay, yeah, so I think we can say that, right, it's going to be designed for a sort of special purpose. And I think often you want to mention the hardware as well. So to be an embedded system, basically it's just going to need the von Neumann hardware. Oh, yeah, okay, so it's going to need the von Neumann hardware. Right, so that's going to be what, a processor. It's also going to be memory, I guess, well, memory / storage, right, and also an input output. Right, so let's say, yeah, okay, what is designed? Right, it's designed, right, for a, for a specific purpose. Right, let's say what, software, right, software and hardware. Alright, yeah, right, okay, so when I say that, I'm talking about kind of specialist software, obviously, yeah, the ATM software, obviously, again, kind of specialized hardware, right, things like the sort of keypad, right, the touchscreen. Yeah, I mean, I guess other ATMs, okay, right, so this one also has the sensor. I mean, other embedded systems are probably sort of more specialist, really. Okay, so it's designed for a specific purpose. Right, let's say that's hard. Yeah, that's hard for people to change. Yeah, hard for people to change. Right, okay, let's say, yeah, it will also contain, right, it will also contain, right, a microprocessor, or well, yeah, processor, microprocessor. Right, let's see what memory, right, okay, right, so memory slash, right, storage. Right, yeah, and input output. Okay, right, input, yeah, output. I guess what, let's say capabilities. Yeah, so I guess what capabilities, right, or hardware. Right, the ATM has a touchscreen and keypad. The ATM may need to be used by people who are unable to see. Identify one other input device and one other output device that can be built into the ATM to help with people that are unable to see. Right, so I guess really this has to be audio then. Right, so input audio, well, we can just go microphone. And of course, well, output audio, well, I guess speaker. Right, then 5, a computer is connected to a network. The computer has a network interface card, NIC, right, that has a media access controller or MAC address. One purpose of the NIC, right, the network interface card, is to provide the computer with a MAC address. Describe the other purpose of the network interface card. Okay, so so purposes, right, plural. Right, so what we can say, well, one is going to allow the device to connect to a network. I guess if it was a WNIC, right, a wireless network interface card, right, then it can also connect to a wireless network. I think here they're probably assuming that this can also connect to a wireless network. Alright, so what we can say, so one is going to allow the computer, the device, to connect to the network. Right, it's also going to handle sort of basic things, let's say encryption, decryption. It's going to handle, I guess, converting the signal from a digital signal, obviously coming from the computer, right, to an analog signal, for example, as kind of like radio waves, for example. Right, okay, so it's also going to do the opposite, right, when the signal is coming in. So if, let's say, it's receiving some analog signal, or if it's receiving some, I guess, kind of electrical analog signal, right, or sort of, radio wave analog signal, well, then again, it's going to convert that back to a digital signal. So yeah, let's try and mention some of those. Let's say it will allow, the device to connect to the network. Connect to the network. Right, let's say, I don't know what, handle communication. Yeah, I think that's okay, right, let's say handle communication. Yeah, we can say what, perform encryption, decryption. Right, encryption, and decryption. Right, encryption and decryption. Right, and I guess what, converting between analog and digital signals. Right, yeah, let's say that, and convert. Right, from analog signals. Right, analogs. Right, let's go digital. Right, so from digital signals. Right, digital signals from the computer. Right, let's say to, I guess what, analog signals. Right, analog signals, I guess what, sent physically. Sent physically. Let's say, well, I guess e.g., right, as, I guess, what kind of electrical signals on a wire. I guess what, electric, well, I guess what, electric current, or, kind of electric voltage. Right, okay, let's say what, electrical signals, right, on a wire. Right, or I guess what, sort of radio waves. Radio waves. Well, I guess, if it has wireless capability. Because I think in this case, even though they do just call it a NIC, so obviously, NIC, probably they are talking about a WNIC as well. But yeah, maybe for IG, they just kind of simplify it down and sort of just have one of them. Alright, but for AS, they would actually kind of, specify the difference between what WNIC, right, wireless NIC, and obviously, just, network interface card. Alright, anyway, so then we want to identify 3 characteristics of a MAC address, so basically talking about the format. Right, so here we can say what is going to be 48 bits. Yeah, 48 bits. Yeah, I mean that's probably okay. Let's say maybe organized, or okay, actually let's say represented. Alright, so actually I'm thinking maybe I don't want to say represented as 12 hexadecimal characters. Or in fact, yeah, okay, alright, okay, yeah, so let's do that here, because I was thinking maybe that'd be the second point. Right, so, okay, 48 bits represented right as 12 hexadecimal characters. Right, okay, then we can say I guess the characters are separated by a colon or hyphen. Yeah, I guess they're in pairs. Right, let's say that, right, 6 pairs right, of hex characters. Right, let's say separated. Alright, separated by. Alright, and I guess usually it's colon. Yeah, colon. Obviously colon being this one. Yeah, or hyphen. Yeah, so actually Macs are kind of weird where you can actually use either of these symbols. Right, and then I guess for the last one, we can maybe say what the first 6 pairs. Yeah, okay, sorry. Okay, so the first 3 pairs, right, or the first 6 hexadecimal characters, they're going to represent the manufacturer or the vendor ID, right? And then the last 6 hexadecimal characters, right, they're going to be unique for that particular product, or yeah, okay, for that particular device. Let's say that, right? Okay, first 6 hex characters. I guess represent the vendor or manufacturer ID. Yeah, okay, right, manufacturer ID. Right, let's say, yeah, and last 6. I don't know, yeah, are unique to that device. Yeah, okay, okay, so I guess technically they're not really unique to that device. What we would say, well, the combination of the first 6 and the last 6 is going to be unique. But you could have a situation where, I don't know, okay, so let's say the first 6 characters could be like 6 A's. And I guess, yeah, okay, alright, so, okay, yeah, okay, so let's just do all of these. Right, and let's say, I don't know, yeah, the last 6 are also like 6 A's, for example. Okay, right, so I'm not going to do all of that. Right, so what we say, well, the first 6, right, that's going to be the manufacturer. Okay, the last 6, well, that's going to be the, device ID. So what you could have is, let's say, another company, and let's say this company, they have sort of 6 B's. Right, so obviously here the manufacturer ID is different, right, but you could have the same combination of 6 A's here. Alright, so hopefully that, okay, so hopefully that makes sense. That the last 6 don't have to be globally unique, right, but it's going to be the combination. So the combination of the first 6 and the last 6, okay, so then they will be globally unique. Right, the network allocates an Internet Protocol IP address to the computer. Tick one box to identify a valid IP version 4 address. Right, okay, so in IP version 4, there should be 4 groups. Each group is going to be separated by, well, I guess a dot, right, full stop, period. Right, each group is going to be a denary number in the range 0 to 255. So if we look at the first one, well, here it's using right, colon, which of course is wrong. Here we look at FF, I mean, that's probably going to be hexadecimal. Right, if we look at the next one, so yeah, I guess here there's 4 groups. Okay, this seems correct. Yeah, all the numbers are in the valid range, right? It's also using dots, right? Okay, so this seems correct. Right, but I'm going to check the last one just in case. Right, so if we see here, well, here we have 5 groups. All right, so since there's 5 groups, yeah, it's obviously wrong. Right, okay, then we want to identify the device on a right, so identify the device in a network that can automatically assign an IP address to a computer each time the computer connects to a network. Right, so actually, really that's going to be the DHCP server. Although this one I did check in the mark scheme, and the mark scheme just says router. Actually, looking in the book, they do say DHCP server. Now, the reason they say router, I guess they're just trying to simplify it. Because actually, if you think your home router, well, your home router is going to include a DHCP server. It's also going to include, right, a bridge, a gateway, a switch. Yeah, I guess it's also going to have, well, NAT, right, network address translation. It's going to include, also DNS server. Right, so that's the thing, that a home router is going to include all of this functionality built in, because really, I mean, people don't want to have 6 different devices in their network, to allow them to connect, or in their home. That's why it's sort of all built into one device. Now, if people do want to see the difference between those devices, I do have some AS videos for that. I would really recommend, there's a good channel, I think it's called PowerCert. So it's like this, right? So PowerCert animated videos. Search, right? CERT. So if you search, right, PowerCert animated videos, right, router, bridge, gateway, switch. Basically, they have a video that just explains the differences, right, between all of those. Like a sort of 5-6 minute video. Also good animations, right? It's kind of easy to understand. All right, so what I'm going to say DHCP server, because the thing is, if you give more detail than required, according to the mark scheme, okay, so if you give more detail, then they will accept that. So let's say DHCP server, and I'm going to put in brackets, right, so built into the, I guess what, home router, or built into the router. So let's be more specific, right? Let's say built into the router in, I don't know, home, I guess, office, right, settings. Because technically, actually, a router, all that's used to do is basically, so as we said in the previous question, it's going to take the packet, it's going to look at its routing table, and then it's just going to forward it onto the next best device, right, the next hop. Now, let's say if you have a router at the sort of bottom of the ocean, right, where you have a cable that splits, going from one country to another, well, of course, that router is not going to need a DHCP server, right? That router is not going to need a wireless access point. All right, so in that case, a router is kind of only a router. But when we're talking about like a sort of home router, office router, well, then again, it's including, okay. So again, a home router is including the functionality, one, of course, of a router, but also of a switch, a DNS server, DHCP server, probably wireless access point, bridge, gateway, kind of all of these different devices. Right, anyway, the next one, so a user accesses the World Wide Web using a web browser. Define the term World Wide Web. Right, okay, that's going to be what the collection, and I think this is really a definition you can sort of remember, it comes up quite a lot. Right, the collection, right, of all, the interconnected web pages. Okay, I think that's okay. I mean, we could mention, I guess, they're sort of written in HTML. I guess what written, right, in HTML. Okay, I think that's fine. Okay, so I guess really the World Wide Web, I mean, you can probably also include that as sort of like the images, the PDFs, right, the, I guess audio, video. I guess that would also really be kind of included in that. Okay, then it says the Uniform Resource Locator URL for a website includes the Protocol Hypertext Transfer Protocol Secure, or HTTPS. And we want to explain how HTTPS makes the transmission of data secure. Okay, so this is a bit tricky. Right, let's try and just draw a simple diagram. Maybe I'll sort of do it, okay, I guess up here. Right, so you're basically going to have two people. Okay, you're going to have the client, so that's of course us, right, the web browser, right, the person trying to visit the website. Then you're going to have the server. So what's going to happen, the client, well, they're going to basically send a request to the server, or asking for the server to send their digital certificate. So the server will send the digital certificate, let's say I guess DC, right, digital certificate. Right, in this digital certificate, there's going to be a few things. Right, one, there's going to be the digital signature. There's also going to be the public key. Alright, and that's going to be the public key of the server. Okay, and the reason why they have the digital signature, a digital signature is to verify, let's say to verify the, I guess, well, the sort of person that sent it. Okay. Yeah, let's say these digital signature is used to authenticate, that the person is kind of who they say they are. Okay, because what you're going to do is a digital signature, well, you're going to use the private key basically to, well, kind of, sign this message, all right? And then the client or the sort of receiver, well, they're going to use the public key, right, from the sender in order to verify that this message came from the person who said it did. Because let's say, for example, okay, so the so the server, well, they're going to have a public and private key pair. Now, if you have a message, okay, signed with this private key, well, then it can only be verified, okay, using the corresponding public key. So what this basically proves is that, so if you have a message, of course, that's signed, well, when you then try to verify, okay, using the public key, well, if it successfully verifies, well, then you know that the person that kind of, sort of signed it, well, they must have had the corresponding private key. And since only they have the private key, so since they only have the private key, well, then it kind of came from them. Right, so that's going to be one thing, the digital signature. Okay, right, then I guess we can talk about encryption. And you can say, okay, well, data is going to be encrypted, right, using the server's public key, right? The client will, of course, obviously encrypt it, send it, right? The server will then decrypt it, right, using their private key. And you can also mention, well, that's asymmetric encryption because you have two keys, a public and private key. Right, I would say if that's a bit confusing, honestly, the best way to practice, so the best way to understand digital signatures encryption, right, both symmetric and asymmetric, is basically just to find some websites online that demonstrate this. So type in, let's say, digital signature online demo, or like digital certificate, or asymmetric encryption online demo. And what you can do, well, you can generate a public key, you can generate a private key. I would say probably kind of have two windows open, or two different browsers. So you can pretend this is person A, this is person B. Of course, right, person A is going to have a public and private key. Right, person B is also going to have a public and private key. So if you want two-way communication, right, then they both have to have a public and private key. Of course, what you would do, let's say person A wants to send to person B. So what they're going to do, well, person A would then use B's public key in order to encrypt, right? They would send that. Person B, well, they would then use obviously B's private key in order to decrypt. Likewise, of course, if B is sending to A, well, B would use person A's public key to encrypt. Obviously, A would then use its private key, of course, in order to decrypt. Okay, right, so let's try and explain that. Let's say maybe the client. Let's say, will request, write the server's digital certificate. Write the digital certificate. Let's say which is signed. Which is signed. By what, the server's private key. Signed. By the server's private key. Let's say, the client, let's say will use, the server's, the client will use the server's public key. We'll use the public key contained in the digital certificate. Contained in the digital certificate, let's say to, verify. Verify that they are communicating, with the real server. To verify, let's say, that, they are communicating, with the real server. Right, then let's talk about encryption. So let's say, when sending. When sending. Let's say the client. The client will use the server's public. Here we go. The client will use the server's public key to encrypt. Encrypt what, the plain text. Alright, and actually I think they often like saying using an algorithm, right? So using the server's public key. Let's sort of draw an arrow here. Let's give you and encryption algorithm. And encryption algorithm. To encrypt the plain text, into or to ciphertext. And alright, so let's and transmit that over the network. Right, okay, then I guess we want to talk about decryption. Right, let's say the server, the server will then decrypt, decrypt, right, the message, or well, yeah, all right, okay, let's say we'll decrypt the ciphertext, right, using, well, I guess, yeah, using the same encryption algorithm, right, using the same algorithm, right, and, well, yeah, and its, or yeah, and the server's private key. Okay, yes, so again, quite a lot there, but I mean, hopefully that makes sense. Okay, then it says the protocol is one part of a URL and we want to give the two other parts of a URL. Right, so let's give an example. Let's go, HTTPS, and yeah, I think let's choose a website that, well, hopefully everyone knows. Right, so let's go, pseudocode.pro, and right, let's go, for example, here, maybe just the editor page. Okay, so if we look at this, right, the protocol, well, that's going to be the HTTPS, right, the domain name, right, that's going to be this. So I guess basically, well, just the website name. And technically you can actually sort of break this down further. Okay, so you can say the domain name, and then, well, here, okay, this is going to be the domain extension. So of course, well, .com, .pro, .co.uk, right, .org, right, .edu. Right, and then the last part, well, that's going to be the, so actually here they sometimes call it, right, path, I guess, file path. I think maybe Cambridge, they even call it, like, file name. Alright, so I think what I'm going to do, well, let's go the domain. Alright, and I think I'm just going to call it file path. So hopefully that's not too difficult. Then 6, a search engine uses artificial intelligence, AI, to identify the most relevant web pages for the user. Right, one characteristic of AI is the ability to learn, and we want to identify 3 other characteristics of AI. Okay, so I think AI, there's, what, 5 characteristics. Of course, well, one is learning, right, as they've mentioned. I think another one, you can say, what, problem solving. Right, and I'll probably give a definition for these, give an example, right, problem solving. Right, I think another one, well, let's say reasoning. Right, I think another one is going to be perception. And, right, finally, we can just go linguistics. Right, linguistics. Okay, right, so if we say problem solving, now, I mean, alright, so I think when it says identify, I mean, we don't really have to give a description, although, yeah, I'm going to do it anyway. Right, okay, so problem solving, I guess we can say when you have, like, alright, so let's say when it uses its, sort of training data or its, neural network, to try to attempt a novel problem that is not seen before. Let's say that. I know, using, using, I guess, what, its model, right, slash, I guess, well, neural network. Right, using its model slash neural network, right, to, I guess, try, right, to try, to, right, to try to solve, I guess, or attempt, right, a novel problem. Right, a novel problem, it's not seen before. And I guess, okay, so I think everyone should be familiar with this. I'm pretty sure everyone has used, ChatGPT or whatever, where, so you can ask it things it's never been asked before, and, it should still be able to give you a, sort of fairly good answer. Right, reasoning, I mean, actually, reasoning is quite similar. So you can say, performing like a kind of step-by-step, sort of, I don't know, kind of series of steps in order to arrive at the conclusion. Let's say that maybe performing. I don't know, performing, I guess, what, sound, or kind of, like, legitimate. Right, sound, I guess, what, logical steps. Right, sound logical steps. And explaining. Maybe let's say, right, and explaining, how it arrived at this conclusion. And to be honest, I mean, okay, so some AI can obviously explain how they arrived at their conclusion. If you look at a lot of the LLMs, right, the large language models, right, most of them can do that now. I guess some other AI, like maybe a self-driving car, maybe that's not going to tell you, why it sort of made this decision. Although, okay. Although probably actually for the developers, they probably can actually see that. They probably do have a way of kind of debugging, right, why it's making that decision. Right, so perception, basically that's kind of a understanding of its surroundings. And either that can be a physical environment, so if you think, well, a self-driving car, I guess like a plane, right, autopilot. Right, so a self-driving car, well, that has to be aware, okay, right, is there another car in front, right, is there a person? What's the, like, road surface like, maybe? What are the weather conditions, right? Because you think, well, if it's raining, right, then it knows, it's not going to be able to stop as quickly. So we can say that, let's see, right, awareness. I guess, right, of its, let's say physical. I guess physical, or... okay, so, okay, I'm not really sure how to explain this. Right, so what I want to say is that you can also think, well, it's going to have a perception, let's say, of society, right? It's going to have a perception of, let's say, the current scientific knowledge, for example. So if you ask it, right, some, sort of question about science, well, then it should be able to explain to you, giving its, sort of perception of the current understanding of the field, for example. Awareness of its sort of physical, / maybe like societal, I think that's probably okay. Right, societal, let's say environment. That seems okay. Alright, and then, so here, even though it says 3, let's do 4, right, just for the video. Right, so linguistics, basically, well, that's LLMs. So you can say, well, it should be able to understand, okay. And actually, the key thing here, okay, not every AI needs to have all of these, functions. Obviously, some AI is going to have some of these functions or some of these characteristics. Obviously, other AI, they can have different ones. Right, so linguistics, if we're thinking LLMs, well, that should understand language that the user has input, and either that could be as text, right, or it could be, for example, audio. I guess it also could be images, right, so something like OCR, right, optical character recognition. It can, scan the image, right, recognize the text, understand what that's actually saying. And then likewise, it should then be able to kind of generate a response, again, either text, audio, image, using, for example, grammar that's correct, spelling that's correct. So basically it should just have a kind of, understanding of language. Right, okay, then B, the search engine uses machine learning. Explain how machine learning is used by the search engine. Okay, so probably you can mention it will be like a recommendation system. So you would say based on previous searches, it will find, for example, what the users clicked on, and based on what users, okay. So let's say based on what links were popular before, well then it can kind of increase their ranking right in the in the sort of search algorithm. Right, you could also mention you can get different results, for example, based on your country. You can get different results, even, for example, I guess, based on the sort of date, right? So I think, for example, yesterday, there was a big earthquake. So if you type in earthquake, well, then of course you're going to get relevant news, related to that earthquake. I know, for example, if you're in, say, so let's say if you're in the UK and you type in football, well, then of course you're going to get results about, let's say, English football, or sort of, football that most of the world calls football. Whereas let's say if you're in America and you search football, well, then you're going to get sort of like NFL, right, American football results. We can kind of say this. Let's say, maybe based on, let's say based on previous data. Or in fact, actually, let's say a model will be trained. A model will be trained. Based on, I guess, what previous user data. Previous, let's say what user data. Let's say search. So let's say search term. Location. I guess even like date. Etc. Let's say and what links they clicked. And what links they clicked. Yeah, I think we could say what to generate a model. Actually, I guess we've said that. Yeah, okay, I think that should be fine. Right, let's say, yeah, to create a recommendation system. Right, recommendation system. Right, okay, let's say what when new users search. Right, when new users search. Right, let's see, okay, yeah, let's see this model. This model will be used. And I guess here you could be more specific. I mean, you could say, okay, yeah, okay, so it could be a model, it could be, sort of neural network. Right, okay, so this model will be used to predict, let's say, yeah, let's see what search results this user would be interested in. Search results, yeah, this user would be interested in. Okay, right, let's say, yeah, I guess what based on, yeah, based on what similar users were interested in previously. Yeah, based on what similar users, right, were interested in previously. Okay, right, I'm trying to think, so is there kind of anything more we can say for that? I mean, so you could mention that it can kind of update based on the user's kind of current searches. And I'm not sure, like maybe this is a new feature that Google's got, because I think recently it seems to improve a lot. Where let's say, for example, if you search, I don't know, like ChatGPT, right? And then let's say if you search how, well, even though this is a completely new search, because it, okay, so because it's sort of, kind of sort of realised that you searched ChatGPT before, well, then your kind of personalised search result is going to be, I don't know, yeah, how does, ChatGPT work, right? How does, yeah, I know ChatGPT get its data. So I think you can also mention that as well. You can also mention maybe, I don't know, search results. Right, search results, I don't know, yeah, will be personalized. Right, will be personalized, right, based on, yeah, based on the user's previous searches. Okay, yeah, so hopefully that should be enough. I would say for this question, right, check the mark scheme, yeah, see kind of what they wrote specifically. Right, then 7, programs can be written in a high-level language or low-level language. Machine code is one type of low-level language. Identify one other type of low-level language. Right, okay, so here actually there is only one other, right, that's going to be assembly. Right, then we want to identify the translator that is needed for the type of low-level language you have identified. Okay, right, so here then it's going to be assembly, and the translator, well, it's going to be an assembler. Okay, right, assembler. So, of course, an assembler, well, that's going to translate from assembly to machine code. Now, if we think that other types of translators, well, compiler and interpreter. Now, compiler is going to go from a high-level language into machine code, and an interpreter, well, that's basically going to go from a high-level language. It's then just going to execute, each instruction kind of, well, kind of line by line, right, statement by statement. Yeah, and that's just going to happen, I guess, kind of in like an interpreted environment. For example, yeah, via the Python interpreter, right, the JVM, yeah, Java Virtual Machine. Okay, right then, yeah, a high-level language can be translated into a low-level language using a compiler or an interpreter. Describe the advantages of using an interpreter instead of a compiler during software development. Right, okay, so this is a common question they seem to love asking. Right, I think what they usually say, basically, if you're using an interpreter in development, well, if you make a mistake, you don't have to recompile the whole program. You can, for example, just go to the sort of point where the error was. You can, of course, yeah, just sort of change that. Maybe, I don't know, sort of, yeah, change the variable, like fix the syntax error, for example, and then basically just, continue running from that point. And they would say that's going to make development speed faster because, again, you don't have to wait for the whole program to sort of recompile. I guess it's also kind of more flexible because you can, change variables as the program's running, yeah, kind of, etc. Right, so let's mention that. Let's say, yeah, okay, right, let's say, yeah, if there is an error, right, if there is an error, Right, let's give an example, right, e.g., well, logic error, right, logic, right, or syntax error. Right, let's say, yeah, this, right, this can be fixed. Right, can be fixed, I guess, as the program is running. I mean, okay, so to be honest, actually, for a syntax error, this is not really the best example because a compiler is actually going to spot the syntax error, before it even compiles. So you say a compiler is kind of safer in that regard, in that if we get a program that successfully compiles, well, then we can be, 100% sure there's no syntax errors. Actually, a lot of IDEs, for example, the JetBrains products, right? So things like IntelliJ, that can also kind of detect a lot of logic errors. Yeah, so I think kind of what IntelliJ, WebStorm, right, PHP Storm. Right, okay, yeah, this can be fixed as the program, let's say, is running. Well, let's say, yeah, by allowing, right, by allowing what the user, what to change the code. Yeah, okay, right, okay, let's say, what, e.g. variables. I don't know, yeah, variables, I don't know, yeah, like functions. Well, yeah, okay, so actually, right, let's say rather than functions, let's say modules, right, because, well, modules, that includes functions, right, functions and procedures, yeah, etc. Right, okay, let's see what this is convenient. Yeah, this is convenient for the programmer. Right, convenient for the programmer. Right, let's say, yeah, and speeds up development time. Speeds up development time. Right, let's say since they don't have to, right, don't have to recompile the whole program. Yeah, okay, right, they don't have to recompile the whole program. Let's say what, and get the current state, back to the sort of state where it crashed. So you can think, let's say you have like a game, and let's say you have some error, but first you need to play like 20 minutes of the game to get to that point. Well, if you, for example, haven't saved that progress, right, then you're going to have to replay that 20 minutes of game, right, in order to get to that point. Same if you have some sort of typical, I don't know, some like GUI application with like select boxes, right, input boxes. Well, of course, you would have to type in all the same input again. You would have to click on the correct buttons, right, so you can get to this particular point. Right, okay, yes, so they don't have to recompile the whole program, right, and I guess, I don't know, kind of, yeah, get to, let's say, okay, get to the program state, yeah, where the error occurred. Yeah, okay, I think that's okay. I mean, maybe we can also mention it's kind of easy to test out small bits of code. Yeah, I mean, let's try that. Yeah, okay, right, let's say, yeah, it's also easy. Right, it's easy to test, right, small bits of code. Yeah, and I think basically again, okay, alright, okay, yeah, so let's say again, right, without having to recompile. Yeah, I mean, I think that should be enough. Like, a lot of those points seem quite similar, and honestly, it seems like there's not that much you can really write in order to get 4 marks. But yeah, I think hopefully that should be enough. Right, and then I think the final question, yeah, okay, right, so integrate development environments, IDE, provide translators, identify 3 other common functions of an IDE. Right, okay, so I think, okay, actually, some papers, they call it kind of like code suggestions. They also call it, well, context-sensitive prompts. So I'm actually just going to say both of them, right, let's say code suggestions. I guess you can also call it like autocomplete. Right, okay, let's say context, right, context-sensitive prompts. Right, okay, let's say what, Yeah, okay, so again, when it says identify, I think we don't really have to describe, but I'm going to describe it anyway. Right, okay, to, I guess what suggests, like, relevant code the user could type. Yeah, I mean, I think that's okay. Maybe like to suggest, okay, all right, okay, yeah, okay, let's say show, because, okay, so I think when you give these descriptions, I mean, you don't want to use the same word that's, you know, say in the question, for example, yeah, or in this case, I mean, don't use the same word that's, yeah, kind of in the name of the thing we're describing. Okay, let's say to show, I guess, what valid, yeah, code, I don't know, yeah, that they can enter or something. Right, yeah, that the user, right, can enter. Right, okay, let's go to the next one. We can say, I don't know, like, kind of, okay, right, so I think this, again, they use various names. You can say syntax highlighting, right, syntax highlighting, I guess pretty printing, although pretty printing, usually that's more in regards to kind of auto formatting, for example, fixing the indentation, yeah, kind of adding the correct spaces. Right, and actually now, I mean, if you go to Pseudocode Pro, I mean, that also has kind of pretty printing built in as well. Right, yeah, that's a new feature. Right, okay, let's go syntax highlighting. Right, syntax highlighting. I guess what we can say, I don't know, yeah, color coding. Right, color coding, and we can say what different token types. Right, okay, different token types. And when we say tokens, basically we mean, well, right, okay, so we mean kind of like keywords, variables, let's say kind of functions. So all of the sort of different types of words that you can type, things like punctuation, operators. Let's say that, right, so keywords. Right, keywords, I guess, let's say identifiers. So identifiers, well, that's any kind of name, right, variable name, function name. I don't know, yeah, let's say operators. I don't know, yeah, etc. Right, and then I think the last one, I mean, let's go maybe a debugger or kind of debugging features. Right, and we can say, I don't know what, that can include a breakpoint, so we can add breakpoints to pause the program at that stage. We can also, for example, see the report window. So the report window, that's going to have the contents of all of the variables. So when we pause the program, well, the report window is going to show the variable contents at that particular time. Yeah, and I guess also single stepping. Okay, so we can just execute, you know, one line, then the next line, the next line. So just kind of executing, right, line by line, just to actually see, you know, how each line is actually affecting it, and hopefully then, you know, trying to find the sort of line that's causing the error. Right, let's say, I don't know, okay, let's say includes. Right, includes features, right, because I think here we don't really have space to describe them. Right, features like, let's see, what breakpoints, right, breakpoints, what single stepping, right, single stepping, yeah, let's say, and a report window. Alright, and let's just check that that's everything. Yeah, okay. Alright guys, so as always, I think that video's gone on super long, but I mean, hopefully it was useful, and if you have any questions, ask in the comments, and see you again in the next video.